Hi, I'm Amir.
I'm Jim. In this video, we're gonna talk about the Eulers Method.
Here's another way of solving differential equation for Euler's method by using table form. We have example problem. Use Euler's method with a step size of 0.1 to approximate y 0.3 for initial value problem. dy over dx is equal to x plus y and y0 is equal to 1. So our given is delta x, or the step size, is equal to 0.1 and dy over dx is equal to x plus y and y0 is equal to 1. So first thing to do is we will use the given starting point and move a small increment or step size at a time in the direction of the tangent line to approximate to the desired value, which is the x of 1 or y of 1. It says in the problem that our x is equal to 0 and our y is equal to 1. As you can see, our delta x, or step size, is 0.1, and we will move a small increment. So from 0.1 we will just add 0.1. So 0.1 plus 0.1 is 0.2, and which is our increment is the delta x, and from 0.2 we will add 0.1, so 0.3, which is what we are looking for, or our main objective. When x is equal to 0 and y is equal to 1, we will get the value of y when x is equal to 0.1. So dy over dx is equal to x plus y, so 0 plus 1, and we will multiply it by the step size, which is the delta x. The 0 is equal to 0.1, and we will add the current value, which is 1, the current value of y, which is 1. So 0 plus 1 is equal to 1, and times multiplied by step size is 0.1, and plus 1, which is the current y value, so we can get 1.1. And our current value for y now is 1.1. When x is equal to 0.1, so y is equal to 1.1. And now we will get the value of y when x is equal to 0.2. And same procedure, we will x plus y, so 0.1 plus the value of y, which is 1.1, and multiply it by step size, the 0.1 plus the current value of y, which is 1.1. So 0.1 plus 1.1, we can get 1.2 times 0.1 plus 1.1, so we can get 1.22. And the current value for y now is 1.22. And we will get the value of y when x is equal to 0.3. So x plus y, so 0.2, and y is 1.22 times step size, which is 0.1, plus the current value of y, which is 1.22. So 0.2 plus 1.22, we get 1.42, and multiply the step size, 0.1 plus the current value of y, which is 1.22, we can get you can get 1.362. And this is now your current value of y when x is equal to 0.3. So this is our main objective, to get the value of y when x is equal to 0.3. So when x is equal to 0.3, y is equal to 1.362. And that is our final answer. Y 0.3 is equal to 1.362.
2,000 years later.
We interrupt this program to bring you a special report.
Right now, I want to walk you through an example of how to use an Euler's method, so you know how to apply it when you run into an Euler's method problem. For example, you're given the differential equation y prime is equal to 2 plus y of 0 is equal to 0, and is equal to 3. So you need to find the y approaches when times is 3. Y prime is our dy over dt. Normally, with calculus problems, you have dependent variable y and independent variable x. Conventionally, typically, on an Euler's method problem, your independent variable will be t instead of x. So we're going to use t instead of x, just like in the formula. The interesting part of this formula is that it's going to change each time you apply it. So you apply it in multiple times in 6 sessions. And you're always going to be using your previous answer to come up with your next approximation. You'll find the first value, then you will use the first value to find the next value, then next one, and so on. Let's start to break down the formula. Let's start in delta t. We know our initial value here is 0, and the value of y0 is our y sub 0. And the n is the last value that we want to find for t. Okay. And our t sub 3 here is 3. Okay. The formula for delta t, or the h, or step size, is equal to t sub 3 minus our final minus the initial over n. Okay, that is 3 minus 0 over our n is 3. So our delta t, our step size now is 1. Okay, that's right. Our t sub 0 here is 0. Our t sub 1 is equal to our value of t sub 0 plus the delta t. So 0 plus 1 is 1, and then our t sub 2, 1 plus 1 is 2, and our t sub 3 here is 2 plus 1 is 3. So the next for the y sub 0, our y sub 0 here is 0. So y sub 1, y sub 2, and y sub 3. Here we need to find the value of y sub 1. So we substitute all the value here in our formula. So our y sub 0 here is 0 plus function of t sub 0, y sub 0. Our y sub 0 here, our t sub 0 here is 0, and y sub 0 is 0. So what is f? Our function of f is always the right hand side of the differential equation we were given. So our differential equation we were given here is 2 plus y. So our t sub 0 here is 2 plus 0. So 2 plus 0 is equal to 2. And then our delta t here is 1. So 0 plus 2 plus 0 times 1 is equal to 2. our next step is to find the y sub 2. To find the y sub 2, we need to change the y sub 1 into 2, y sub 0, 1, t sub 0, 1, and y sub 0, 1. So, we need to substitute all the value here for the y sub 2. Our y sub 1 here is equivalent to 2, plus the function of t1, y1. Our t1 is 1 and y sub 1 is 2. So, need to plug in here. Our t sub 1 here is 2 plus y. Our t sub y, our y1 is equivalent to 2. So, 2 plus 2 is equal to 4 times 1. So, our value of y sub 2 is equal to 6. And for the y sub 3, just like we did, we changed the value of y sub 3 is 1, y sub 2, t sub 2, and y sub 2. So, our y sub 2 here is 6, plus function of x, t sub 2, y sub 2. We don't have t sub 2 here, so 2 plus the value of y, which is 6. So, 2 plus 6 is equal to 8. And the delta t, which is 1. So, 6 plus 8 is equal to 14. And this is the value that we are looking for. So, our y sub 3 is equal to 14. And that's it.
Another one.
The last thing that we want to discuss is the accuracy of Euler's method, whether it will underestimate or overestimate the actual solution, and how accurate in general the approximation is going to be. If your solution curve is concave up, just like this one, an Euler's method is going to underestimate the actual value. We always start our tangent line from the initial point right here, and the tangent line looks something like this. So when that's the case, you might be trying to find an approximation for the solution. Let's say at this point is your t sub 1. The corresponding point t sub 1 along the tangent line is right here. So obviously, the tangent line value is going to be less than or lower than the actual value. Always remember that when the solution curve is concave up, you can always expect that the value along the tangent line is lower than the actual value. Contrast that in a solution curve that is concave down. As you can see, the point along the tangent line, or the approximation point, is above the point along the solution curve. It means that in a solution curve that is concave down, you can always expect that your approximation is always greater than the actual solution. How accurate is Euler's method? As you can see, the value of your approximation is 10, and the value along the solution curve is 8, which is the exact value. So, there's an error. How do you compute an error? This is how we calculate the percent of error in Euler's method. Error is equal to actual value minus approximated value over actual value. For example, percent of error is equal to absolute value of 8 minus 10 over 8. 8 minus 10 equals negative 2. The absolute value is positive 2. So it would be 2 over 8, or 1/4, or 0.25 times 100. So your percent of error is 25%.
A few moments later.
Thanks to Sir Leonard Euler, who introduced to us the nature in solving such differential equation.